like there's three of them, right? Like we have a vertical tangent here, we have another one right here, and then we have a one right over here. So when we do this, more than likely we should get three different answers, all right, when we're trying to find these vertical tangents. So that's kind of our process. So what this gets at, it makes you make a couple of connections with some things. If we're looking for vertical tangents, one of the jumps that should immediately take us to, the only time we've ever referred to vertical tangents, we talked about that being a place where our derivative, one of the three places where your derivative is undefined. So discontinuities and sharp corners are also options. But if we have a vertical tangent, it's really asking us to figure out where is our derivative undefined at. So what we talked about yesterday, and it popped up a little bit with parametrics, if we want our derivative to be undefined, if we want dy dx to be undefined, remember how we found dy dx yesterday? We needed to take dy d theta and divide that by a dx d theta. So when we now look at it as this fraction right here, and we start asking, well, what's our next step? What can we get started with this idea that our derivative is going to be undefined? Well, if I have this fraction, what would have to be true if this derivative was undefined? What would make this thing be undefined? Right?
dx d theta equals.
Good. That denominator of dx d theta would have to be equal to 0. You're going to get some non-zero number up here, and then we're going to be dividing by a 0. So what this question is really asking us to find is where does, and this is what Brian said, where does dx d theta equal a 0? We talked about yesterday, you can memorize the dx d theta, the denominator, or just understand all that really is the conversion that x is equal to, let me rearrange this a bit. That's what I want. That x is equal to r cosine of theta. So if I want the derivative of this, I'll get the dx d theta, and then we just take the derivative of r cosine theta with the product rule. So when we do the product rule, the derivative of r would have been r primed. Leave your cosine of theta alone. Product rule we add, leave the r alone, and then the derivative of cosine ends up being a negative sign. So this ends up being a minus sine of theta. If you have the formula remembered or memorized, you have it on your paper right now, all we are really doing is taking this denominator and setting that equal to 0. So if you have it memorized, that you can just jump right to that, but that's ultimately what we get here. So now take that, set it equal to 0. At the same time, let's plug in the things that we need. So we definitely need an r primed, right? So here's our r prime. So r prime is nothing more than the derivative of the original function. So right underneath that, r prime in this problem is a positive sine of theta. So in this spot right here, you're going to do sine of theta. And then we would want the cosine of theta. And then we have the minus sign. And then we want minus r. R is just the original function, 1 minus cosine of theta. And then times that sine of theta. And these are more like some of the longer, harder trig equations that you would have dealt with a little bit last year. We need to solve that equation. So to solve that, we certainly want to simplify the right-hand side. So as we go through this, the sine theta, cosine theta, not a whole lot we can do with that. So we're going to recopy that. Then let's just treat this as a negative sign. So we're going to take a negative sine of theta and distribute it inside of these parentheses. So a negative sine of theta times 1 would just be a negative sine of theta. And then the negative and the sine of theta multiplied by a negative cosine should give us a positive sine theta cosine theta. Then you hopefully notice you have some like terms here. Here's a sine theta, cosine theta. Here's another sine theta, cosine theta. So that is a 2 sine theta, cosine theta. And it's probably been a very long time since you solved these trig equations, but these actually solve very much like variables where you would need to factor these. So notice how you have a common factor of sine of theta. We want to pull that out. And then you're left with 2 cosine of theta minus a 1. You don't necessarily need to copy this next step down, but this is really nothing more than some zero product property stuff, right? Like when does x equal 0? That's one solution. When does x minus 4 equal 0? That's another solution. We're just doing that now with trig functions. So one of our solutions should be when the sine of theta is equal to 0. And then our other solution should be when 2 cosine of theta minus 1 equals the 0. So think about our unit circle. If nothing else, this polar stuff really makes you know your unit circle pretty well and recall all of these things we haven't talked about in a while. On our circle, this is asking you, sine is your y coordinate, so the y coordinate of what angle equals 0? So that should happen here at angle 0. We also get a y coordinate of 0 at pi. And then wouldn't this go on forever and ever? 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, so on and so forth. So it's important to understand our interval. We only want to stay between 0 and 2 pi. Those parentheses are there intentionally as well, so we're not going to worry about the 0 and the 2 pi. So of these, for sure, we would never go into the 3 pi. But since it's an open interval, we're going to not worry about 0 and 2 pi as well. So one of our answers is definitely the angle of pi. If we look at our graph, almost certainly this point right here. So that's one of our vertical tangents on this graph. We have another equation then to solve. So now these simple little equations are when we now want to isolate our trig function. So subtract or add that 1 over. What the solution to this would be is the angle whose cosine value is a 1/2. So if we now look at our circle down here, we're trying to figure out cosine is your x coordinate and what angles have x coordinates of 1/2. So we again reviewed these yesterday when we were graphing them, but these should be all of our pi over 3s. So pi over 3 up here, that has an x coordinate of 1/2. This pi over 3 would as well, but x would be negative over here. This pi over 3 angle down here, the 4 pi over 3 would be, but that's a negative 1/2. And then our other one should be this pi over 3 angle in the fourth quadrant. That should have a positive x coordinate of 1/2. And again, we don't deal with these a lot. Anybody know what the 5? Oh, I just said it. Shoot. Never mind. I was going to see if we knew what the fourth quadrant pi over 3 angle is. It's 5 pi over 3. Those are our other two answers. And what those are going to give you then almost certainly is this vertical tangent here, this vertical tangent right here. Notice how we would have had an issue too at 0. It's a sharp corner / vertical tangent, one or the other. That would have been covered if I wrote the interval correctly. We just ignored those because of the interval, but that would have both been those 0s and the 2 pi's. So in this case, our answers are those 3 angles, okay? Really common question. You will see that in your future, okay? I promise. All right, so that's that. That's the derivative and graphing of those. And then now today, if you have your calculators, pull those out. You're going to want to have those. And then actually, I didn't actually show you how to graph in polar just yet. You're going to need to know that, so I'll show you that in a minute. But kind of the last thing in this chapter is we've done the derivative of polar graphs, and then now we just want to be able to do the integration of polar. So what this is based off of is the area of a sector. So old idea, area of a sector. In all honesty, I'll kind of sketch it out over here. I think it's easier to think of this in degrees. So if you think about what an old sector is, it's basically a piece of a pie. So if I have a circle, I can draw in the circle. Easier said than done. All right, so if I had that circle, and let's say we just wanted to figure out only a piece of that circle, piece of this pie right here. Let's say this is 0 degrees, and let's say we went up to 60 degrees. Let's say I tell you that our radius is, we'll say 4, and I want you to find the area of that sector. All right, pretty straightforward with the understanding that you would have to do the area of the overall circle first. We would want to know the formula for the area of a circle, pi r squared. And in this case, we know our radius is 4, but that assumes we have the entire circle. We would know then if we're going to do this in terms of degrees, 60 degrees, we want to know what fraction does 60 degrees make up of the entire circle. So 60 degrees, we would divide that by 360. And what we would be looking for, the full circle would have had an area of 16 pi. We don't have the full circle. When we do 60 divided by that 360, we have 1/6 of that area. So that would give you 8 pi over 3. That would be the area of just that sector. All right. You got to treat your calculator better than that, Andrew. You know. So here's how we basically have just done this and where this formula comes from. Here's the area of a circle. So that's what we would have done first, just knowing the area of the overall circle. When we start dealing with our trig stuff, we want to be in radians. So all I did is I took this angle of 60. I did it in terms of degrees, but whatever that angle is in radians, we would then divide by 2 pi radians. That then gives us the fraction of the circle that we're looking for, the piece of the pi. In this case, it was 1/6. When you look at that, then the pi's would cancel. So those are just going to go away. And what you were then left with is the 1/2 of theta multiplied by r squared. That simplifies to being this as the area of any sector that we want. It's always 1/2 times the theta multiplied by your radius squared. I think you've seen that before. It's just you probably haven't dealt with it a lot, but that's the area of a sector. All right. So what I want you to do down here, draw in another circle. Fix this. So draw in another circle and let's go to pi over 3, or pi over 6, and then pi over 3. We want to find the area of this sector, and we're going to say that our radius, what did I let it be? I let it be a 2. And we're going to do it a few different ways. All right. So the area, the first way, so option number 1 here, is kind of what we just did at the top, and that's the simple, let's do some old geometry, pi r squared. Let's not overthink it and use some fancy sector formula. That I know that the radius of this is 4, or there's 2. So I'm going to do 2 squared, which is 4 pi. And then what I would simply now want to do is figure out how much, what fraction of the circle do I get. Think in terms of degrees. I think it's easier to do the fractions this way. But this is basically a 30-degree angle to a 60-degree angle. So in here, 30 to 60 means we are dealing with a 30-degree angle. So we would have 30 of the possible 360 degrees all the way around a circle. So we're going to take our 4 pi, multiply by 1/12. The area of that sector would be pi over 3. So that's old pi r squared stuff. Option number 2 is to use our new little formula here, that the area of a sector should be 1/2 of our theta multiplied by our radius squared. What I'm going to have you do before you jump ahead here, rewrite this real quick with the r squared first and the theta second, just so we can transition to kind of what we're going to be doing here in this set of notes. Then again, don't skip ahead too much. You're going to have your 1/2. Our radius is still 2 squared. And our theta, the way I'm going to have you write this is we're going to do kind of what we did to figure out this was a 30-degree angle, a pi over 6 angle. Take pi over 3, the bigger angle, and subtract pi over 6. What that should leave us with is 1/2 of 4 This would be 2 pi over 6 minus a pi over 6 if we got common denominators. So 2 pi over 6 minus a pi over 6 is pi over 6. So doesn't that then give us 2 pi over 6, which is also pi over 3. So we get the exact same answer doing it that way as well. Third option, let's write this as using an integral now. And we're going to kind of focus in on this one right here. So the very, very, very first integral that I ever had you evaluate, remember if I gave you, let's say we'll go 2 to 5, you don't necessarily need to write this part down, and then 4 dx. Remember how we said we really just do 4 and multiply it by the difference in x, which is 3. That integral has a value of 12. We can do the same thing with this. And that's sort of what I have highlighted in yellow right here. That's the one we're going to kind of focus on. The 1/2 is a constant in this one. So we're going to leave this as a 1/2. The radius is going to be 2 squared. And the reason I wrote this as the difference in our angles, write this as a d theta, because that's really what that stands for, is the difference in our angle, whatever that difference is. But when we wrote these as integrals, where we actually put the difference in the integral is right here for your lower limit, pi over 6, and your upper limit, pi over 3. So if I now ask you to evaluate that integral, it better give us this pi over 3 that we got using some geometry, old geometry, and then some new geometry with the area of a sector. So if we now do this as a little review, this is 4, right? So this is 4 theta. We're going to evaluate it from pi over 6 to pi over 3. I'm going to go ahead and pull the 4 out with the half, so I'm just going to get 2. And then all I'm really doing is pi over 3 is the upper limit plugged in, minus pi over 6 is the lower limit plugged in. Again, pi over 3 is 2 pi over 6 with a common denominator. So 2 pi over 6 minus a pi over 6 is just a 1 pi over 6. And we will once again end up with pi over 3. So the way these get set up when we're dealing with an integral is what we have right here. And that's what you're going to see at the bottom, that's the middle of the page. If we want the area of a polar sector, it is nothing more than 1/2 multiplied by r squared and then multiplied by the change in your angle. Okay, so we're going to usually put the half out in front. We'll integrate from whatever angle 1 is to angle 2, and then it's going to be r squared times d theta. Okay. Now, I want you to know how to graph these. It's not terribly important we know how to graph number 1, but in a second, you're going to need to know how to graph these. So let's graph this on a calculator. So to do that, same place where we change from parametric or from function to parametric. So right down here, most of you are in function most of the time. We've already changed into parametric. You can see what I have highlighted is polar. So we just need to move on over to polar. Hit enter. And when you now go to your graph, it should look like the stuff we were doing yesterday. We have an r, and it now equals whatever. The equation I wanted you to graph was 2 and then 1 plus cosine of theta. So plug that in, and then very cutely, when you hit your variable key, you're going to see a theta pop up. Oh, I got a little too anxious, so I forgot the cosine. So cosine theta, and when we graph that, that's what that would look like. Your windows, make sure you go 0 to 2 pi so that we get all the way around. Your windows will look a little bit different as well. So make sure you have at least 0 to 2 pi. 6.28 is 2 pi. As long as your theta step is tiny, then you should be good. Doesn't necessarily have to match mine, but it should look like that. All right, y'all got that? All right, so what we're looking for is the area of that figure. So for the sake of this first one, I'm going to go ahead and sketch this. This is basically just a bigger version of one of the cardioids that we did yesterday. So what I said right here, if we look at what I have highlighted, what I'm circling now, the area of the sector of a polar curve, or the area of a polar curve in general, is 1/2 times the integral of r squared. It doesn't get any easier than this, right? Because there's an r given to you. It's flat out, here is what r equals. I'm going to distribute as no, I won't. I'll make it look like this. So 2 times 1 plus cosine of theta, that is r, times our d theta. And then we just need our angles. That's why I like doing these by hand first and going all the way around. If I start with angle 0, which is what we're going to start with, so make your lower limit of 0, and I'll kind of explain. That would give us the length of this r. So that would give us this. Well, if I then go to pi over 6 and all the angles in between, that would get me to pi over 6. But then I need to go to pi over 4, pi over 3, everywhere in between. Here's pi over 2, here's pi, here's 3 pi over 2. We need all of these until we get all the way back to 2 pi. So our limits are simply 0 to 2 pi. That would give us every radius from beginning to the end around that entire shape. All right. Should be able to do these by hand, but for the most part, very unlikely you would ever be asked to do that. This now just becomes a Math 9 question. You throw that into your calculator for the sake of time. At some point, you probably want to do it. But you should get 6 pi, which means when you throw that into the calculator, what's 6 pi exactly? The calculator will, you might want to check me on this too. 18.850 if we round correctly. All right, as our area then. So if we're just looking for the area of the whole shape, it's pretty nice. Know the formula. Going from 0 to 2 pi, that should give us every r all the way around the unit circle values that we're looking for. All right. Hopefully easy enough there. Number 2, however, remember the ones that have those little loops? So if I were to have you graph this, there's going to be a loop in this. So we'll go ahead and do that just so visually you can see it. So 2 cosine of theta plus a 1. 2 cosine theta. And then not surprisingly, you have that little loop in here. So we only want the area of this little guy in here. That's it. So let me sketch this again, just so when we revisit this, we know what this looks like. So it swings around like this. We have this loop. And we want just this part of it. So to start with, it's pretty straightforward. The area of a polar curve is always 1/2 r squared d theta. R, again, is super easy because you're given it. It's 2 cosine of theta plus 1. So really the only decision making we have in this problem is what angle do I need to start at? What angle do I need to end at? So that we're only dealing with the r's inside of the circle. So yesterday when we did these, this is another reason why I mentioned that yesterday when we were doing that. You see this one a lot. It's also why I like doing these by hand the first time. Remember, when we did these, the reason we ended up with that loop, remember how at some point there was some angle that when I figured out whatever that angle is, that's an asterisk, don't think it's an X or anything. Remember how it would give us a radius of 0? So here I have a radius, let's say this is 2, and then this is a little smaller, a little smaller, a little smaller. This is a radius of 1. Eventually, as I work my way around this curve, didn't we get a radius of 0? Then we got some negative radiuses in here, so negative r, and then eventually, as we worked our way around this loop, didn't we end up again getting another place with a radius of 0? So what we are really looking for is, when does our radius have a value of 0? That's our intent in terms of being able to figure out what our limits are. So we want to know, when does r equal 0? Well, here's r right here. So we basically now need to just take that. Let me have some room to operate over here then. And we need to take that equation, set it equal to 0. these should give us the radius that gets us into there with the first r of 0, and then the last r of 0 that gets us back out. So solve that, subtract your 1 over, divide by 2. Do that real quick. Let's see how good we are with our circle here. So figure out what those angles would have to be. All right, let's see what you got. What we're looking for is the angles whose cosine value, so whose x coordinates are 1/2. So the x coordinate, or the angles whose x coordinates are 1/2, those should be our pi over 3 angles, correct? All right, what do you think they are then, Lily? Good, so we want them to be a negative 1/2. So what pi over 3 angle, because that's our first one in the first quadrant, what pi over 3 angle is in the second quadrant that would give us an x value of negative 1/2? Did you get that? Good. That would have to be 2 pi over 3. And then the other pi over 3 angle should be in the third quadrant. That's the other place where x is going to be a negative value, and that should be what? Good. So those have to be our limits. So the lower limit, the first 0 value is 2 pi over 3. So this would have been a 2 pi over 3. And then this would have been a 4 pi over 3. Everything in between here would have given us these negative r's as we work our way around the loop. And then 4 pi over 3 gets us back out. This is then what you're plugging into your calculator. All right. Make sure you can do this. Don't necessarily take that for granted, but you should get, this is just a little guy, 0.544 for that. No, it isn't. Yes, it is. Yes, it is. Sorry. All right. So now, having done that, 3 is not a surprise. Just now kind of want to see if we understood what we just did here. This is really, you can graph it if you want. But if we understand the area of a polar curve is always 1/2 times your r squared, we can just jump right to all of that. We know what r is, and then times our change in theta. We just need to figure out what is the change in theta. Like what angle starts us inside the loop, what angle is going to get us out of that loop. So see if we can come up that real quick. Let's see what angles we got. So the loop gets us in with an r of 0, then we get a bunch of negatives, we get another r of 0 to get us out. So we're really just taking this equation and trying to figure out when did our radius have a value of 0. So same process as that previous one, you just now need to know some different values along the unit circle here. So we're just thinking on our unit circle, if we're looking for when y values are negative, we've got to be down here in the third and the fourth quadrant. When our y values are going to be negative on our circle. Then we want to know the y coordinates are 1/2 at pi over 6 values. And then it's just a matter of knowing what's our pi over 6 angle in the third quadrant, what's our pi over 6 angle in the fourth quadrant. Again, we don't deal with these a ton throughout the course of the year. All right. What is our pi over 6 angle in the first one? Well,
7 pi over 6.
good. So this would be 7 pi over 6. That's the pi over 6 angle in the third quadrant. And then good. And then 11 pi over 6 is the pi over 6 angle in our fourth quadrant. Now, these are the exact same graph, just rotated 90 degrees. So this would also give you the exact same answer, 0.544. I just wanted to kind of go through that solving the trig equation again to make sure we understood what we just did. All right, good with those? Easy enough, hopefully. All right, next one then. What if we have two curves? So this says the area between curves. You'll see the very first thing I write, very similar to finding the area between curves when we did it before, where we would be doing like top curve minus bottom curve, or the right side minus the left side. There is a little difference here, so you just want to be careful. So it says find the area enclosed by the two curves. So sketch in that space that I left you. What did I draw in? Draw in a circle that looks like this. And then draw in, we'll do a little cardioid that looks like this vertically. And I want the area enclosed by them. So I would be looking for this stuff, area between them, which would be this stuff here. Now, while it is similar to something that we've done in the past, there is some differences. This is going to look very, very similar to what we have done in the past, this option. What we really want to be doing is finding the area of the big polar curve. So we're going to say from A to B, 1/2 r squared. So let me do this one in red, because isn't the red one the bigger value? It's the one bigger. It's the top curve. So I'm going to do r squared and then times our d theta. And then wouldn't we really just then need to subtract the area enclosed by the polar curve? Because if I did that right now, like if I just did this, wouldn't that give us all of this area in here right now over that limit? Well, we don't want all of that. We want to get rid of the stuff enclosed by the black circle. So then we would go from A to B, and we would want to subtract the smaller r d theta. So it looks somewhat like our washers, correct? Are very similar. And that's valid. So we can then simplify that to put the half out in front. And then you're going to go from A to B, and we would just be doing the big R squared minus your little r squared. And then our d theta. Here's where we now need to be careful. Whenever we would have done something in the past, so let's say I gave you this line and this line, and we did the top curve minus the bottom curve, that's top minus the bottom. Where this now gets a little bit different, what we're really always doing, even when we did right minus left, so let's say I give you a parabola that opens to the right, and then I have this vertical line here, we would have done right minus a left. What we're really doing in all of these is we're doing the bigger value and subtracting the smaller value. That's why top is bigger than the bottom, right is bigger than the left. That's what we've always been doing. So here's now where you need to be careful. So let's say I now get rid of this, and let's say I draw this cardioid so that it opens like one we did yesterday, like this. And I now want this area. If I want to set up an integral right now for this guy, and I want to make sure that I'm going to be doing the bigger values minus the smaller values. So if I now do area equals 1/2, and then we'll do our big R squared minus the 1/2 of the, I hope I can squeeze this in here, just a little bit, the little r squared. If this is where we're always starting, when I look out at angle 3 pi over 2 here, what now has the bigger r? The red graph or the black graph? The red one, right? So, because the r, if we drew in a polar graph, the red is actually going to be bigger. So what you don't want to get married to now is top, bottom, right, left when we're dealing with polar. What you really want to think of is the outside curve is going to be the bigger r values. The inside curve is going to be your smaller r values. So that's how we really want to approach this, so that we maintain this idea that to make sure that we always get a positive radius, that we've got to be doing the bigger minus the smaller. Okay? That makes sense? All right, so go to, let's try to get one of these done. Yeah. Here's why it's pretty critical that we know how to graph these now. So go on your calculator. Actually, we know the circle, right? Like this we should know is a circle. R equals a 1. So that I can draw in. But unless you want to spend your time doing what we did yesterday and going through the entire unit circle and trying to graph this, then we would want to be able to throw that into your calculator. So go ahead and graph these together. So one is just circle 1. And then the 1 is 1 minus the cosine of theta. All right, and then we see that we get the cardioid kind of going off to the left there. So we sketch these in. Yeah.
What's the ideal window?
It will vary, but if we know that this is a radius of 1, same over here, like the cosine, if we go way back to like amplitudes, amplitude of a cosine is 1 to -1, and then we have a 1 right here. You can't get bigger than 2 or -2. So I would just, probably 5s are always going to be safe. Okay, I don't know if we're going to get all the way through this one, and I don't necessarily want to rush, but let's talk about 1 and 2 together. And then maybe we'll do these tomorrow. Same exact equations, right? R equals 1, R equals 1, R equals 1 minus cosine theta, R equals 1 minus cosine of theta. So the exact same equations, but understand how these, while they're using the same equation, are very much different. This one is asking us to stay inside of the circle, but outside of the cardioid. So if I ask you real quick, shade this in, are we looking for region 1, region 2 here, or region 3? Shade in what you think we're looking for. Because in the next one, we're doing the exact same graph. So here's my circle. And then here's our cardioid. Not bad. And if I now ask you in this one, or what are we looking for, 1, 2, or 3? We got to identify based upon reading it and understanding what these look like, which one we're looking for. So then shade in what you think you're looking for, number 2, or at least have an idea. You don't want to have to erase something in case it's wrong. Kind of like that baby blue. Easy. All right, so for number 1, if we want to stay inside of R equals 1, and then outside of the 1 minus cosine of theta, what would we be looking for, 1, 2, or 3? Good. We put some 3 fingers up here. So this would be region 3. That's what we're looking for in number 1. For number 2, if I want to go outside of R equals 1, but stay inside of 1 minus cosine of theta, that would now be which region? Good. That should be region number 1. All right, and God forbid I give you region number 2, right? So that's when it gets really tricky and kind of hard. But that's kind of what these are setting up, and I don't necessarily want to rush and then expect you to do a quiz on this tomorrow. So we'll wait on the quiz, and we'll kind of go through these. I'll pull up, these are really common, the free response questions on the repeat test. Did I give you any of those in there by any chance? Do you have any free response? Is that the next page? Okay, then maybe we'll finish these tomorrow, and then I might look at that free response question, and we'll spend the rest of the period kind of going over that. You can kind of see how these get asked on the AP test, okay? So no quiz tomorrow. Most likely we will do that on Thursday, okay? Okay, with that, if you're at home, you guys can take off, and then we'll see you tomorrow. And if you're here, just hang out.